So hello and good afternoon, everyone. So my name is Arvin Escultero, and I'm here to present our study, which is a collaboration between Department of uh, Chemical Engineering at saka yung EEE PEL. So the title of the study is Bandwidth optimization of load following controls for fuel cell and battery hybrid power systems in telecommunication base stations. So a little introduction about fuel cells. So fuel cells are, well, they are a energy conversion device that converts hydrogen fuel or maybe sometimes another source of hydrogen like methanol into electricity. And their byproducts are just water and heat. Now, so unfortunately, there are also some shortcomings with this technology. One being the voltage, which exhibits a high change in output voltage as the power changes from 0 to full power. And it has a weakness in frequent fluctuations in the output power, which contributes to more degradation as it progresses. So a solution to this is to hybridize it. Connect a battery there at the bus voltage that it will serve as the one that will capture the transient load requirements. And unfortunately, it will be an added cost to the system, and battery will still degrade even when partially charged and discharged. So optimizing the lifespan of the power sources will involve allotting which part of the power spectrum will be given to the battery and which part will be given to the fuel cell. So power sharing optimization, so allocating the power demand. So as we can see here on the right side, this is a load profile of a telecommunication base station. Although it's not that erratic as compared to electric vehicles, it still has some fluctuations throughout the day and even every second as the demand of communication changes. Now, so system health must be maximized while fulfilling the output requirements where the output bus voltage must not dip at certain levels where the communication substation will shut down. So there are gaps and shortcomings. First is the optimization studies are usually involved in EVs because, well, that's the trend. And the fuel cell substations, fuel cells in stationary applications are usually just using rule-based approach, which is the cycle charging, where you charge the battery at full capacity and shut it down, and let it drain and sustain that bus voltage. So what we propose is to use the load following controller, which instead of utilizing that standard cycle charging approach, the fuel cell will follow whatever the output demand is required. Of course, you don't want to make it too fast, otherwise it will degrade too fast. So the DC-DC converter must be configured as a current source for this because the battery will maintain the bus voltage. And what we see is an integral controller is more than enough to control the fuel cell's output current because we don't want it to actually respond too fast, right? So adjusting the controller gains, we can actually control the bandwidth and the response of our fuel cell. And the system performance is, of course, finding which part of that bandwidth will it optimize in operation. Specifically, the fuel efficiency, degradation, and the operating cost. So we modeled the system and simulated it in MATLAB, Simulink. So we utilized the Simscape toolbox there, which has a fuel cell and battery model already. So it's just a matter of tweaking it to the way that is actually useful for us. So for the fuel cell, we utilize that model. We entered the parameters, but for the battery, we actually opt to use the table-based approach because the resolutions are just 1 second, and that won't actually be that much detail for the batteries. And of course, we want to simplify it so that the computations and the resources used will not be that much. Now, so what we added in the model is the degradation because we want to actually find the amount which is degraded because it is prone to changes right here from utilizing the load following approach. Now, so there are three major sections in the degradation of the fuel cell. One is the on-off cycling. So every time you turn off and turn off the fuel cell, it will add to degradation. We have duration-based degradation. The moment you turn on the fuel cell, it will already start to degrade by some amount. When you cross the overloading section, it adds another degradation. Underloading, another degradation. And of course, load changing part, which will follow the output load, adds another degradation. So actually, there are a lot of complexities in the degradation mechanism of the fuel cell. And another part of the degradation is the battery degradation, since we want to measure it to the point that it will not cycle it from max to minimum. So we want to create this model so that it will actually account for the AH throughput of the discharge of the battery instead of number of cycles. So here are our source parameters for our fuel cell. So we sized this, but that was another study, so I didn't include that much detail here. It would be too long. So we use a 4 kilowatt PEM fuel cell. For the battery, we used a lithium-ion because of the advent of many EVs. There are a lot of second life batteries available, and they're very cheap. So we use that instead of VRLA lead-acid batteries. So we characterized the performance. So for the fuel cell, we checked which setting for the integrator would create a stable response, and which part would be too slow already that it will drain our batteries. So as we can see here, we used -20, -40, and -60. So they had that response. Fortunately for the -80, which is our slowest response, it already drained our batteries before it reached that set point. So, okay, but we override the program to see if what is the output fuel cell current for that. And we can see the green part right there, it's very smooth. Actually, that's the type of response ideal for the fuel cell. So we modified our algorithm to actually start. Now, so we saw that the weakness was in the startup. So when you start it up, it already drained the battery. So what if we just start it up at max speed and then eventually slow it down in the later parts of the run? At least we can consider that part where it will have a slower response. Maybe it will be okay in the later parts. And we also introduced a fuzzy controller. What if it will be more dynamic instead of that step response? So here are our results. So as we can see, again, it's very smooth already. Unfortunately, it overshot to 1 this time. So again, if we increase the battery further, it will add to a capital cost, and it will be another issue, another problem for that. So it's another consideration, maybe consider for the later parts of the study right there. But for the other parts, yeah, we have that response for the faster response and for the fuzzy. So lastly here, we have the operating cost. So we compared the different load following approach, the acceptable ones, with the cycle charging approach. So as you can see there, a reduction of around $50 in the operation after 4 days when you compare the cycle charging approach with the load following. Unfortunately, when it comes to varying the different bandwidth, the speed of the controller, you can see there's little to no difference there, maybe a few errors, but it's not that significant. So actually changing to load following will already create that much benefit, but when it comes to optimizing it in terms of bandwidth, unfortunately, there's not that much. So actually setting it to load following at a certain stable response would actually benefit the system as is, and further optimization of it might be a bit not that much beneficial. So for conclusion, so utilizing an integral controller is more than capable of implementing the load following control, since we want a slow response. Power fluctuations in telecommunications base stations, well, it's not that erratic compared to electric vehicles, so load following is an acceptable choice for the controls. It will introduce less stress to the battery, allowing longer life and less maintenance replacements. For efficiency, yes, it also improved because there is less excess power that will go to the battery and will require the cycle efficiency. Using load following controls instead of cycle charging will allow for better performance and overall less operating costs. And as long as the system is stable and the batteries are not drained, there's no significant difference in varying the bandwidth any further. And I just want to give thanks to our team, Project Cypher, the Chad Picari project, and I'm involved in. Thank you, everyone.
Are there any questions for Mr. Arvin Escultero? I guess I have one question. Can this optimization be generalized to other kinds of loads? What kinds of loads are most similar to the one you studied, which is telecommunication?
Good question, and actually I want to consider that in future studies where I will introduce other load profiles specifically for stationary applications. No? So, diba, there are a lot of studies involving mobile and automotive applications. But for stationary, we want to actually explore those involving off-grid applications. Maybe it will lead to better, well, most likely we will expect a different result from that. Different size, maybe different bandwidth would be more optimal, or maybe rule-based approach will be better. I don't know. Maybe we can explore that further.
Thank you again, Mr. Arvin Escultero. Now I would like to give this certificate of appreciation for sharing their invaluable insight and work on bandwidth optimization of load following controls for fuel cell battery hybrid power systems in telecommunications base stations.